All right. Hello, everyone. Welcome back to Comp 3430 Operating Systems. I hope that you are all doing really good today. I know that we're in this kind of like cold spell again. It's gotten cold again. It has gotten cold again. However, I will note that when I finally got out of the house this morning after getting up and like feeling like I don't want to get out of bed today, I just want to stay here under the covers where it's nice and cozy. When I finally got out of the house today at 7:30 to take my kids to school, kind of like I noticed at 5 o'clock that it wasn't dark, I noticed at 7:30 that it was getting bright already. Things are getting better. We're working towards springtime. We're going to get there, and I'm really looking forward to that. Let's talk about operating systems. The first thing that I wanted to bring to your attention before we do anything today is that I posted a couple of more volumes to the sample volumes repository. So there's a total of 9 sample volumes right now. If you want, you can download the 2 files. I'll let you know what's in them in just a second. You can just download them directly from GitLab, or if you have this as a repository, you can pull the repository and you should get the new volumes in the directory that you've got. The 2 volumes that I added to the repository are one that's called longname.image. This was a request from someone on the forums for a sample volume that has a really, really long name on it, so that we have more than one file name directory entry. And so this is a really, really long file name. There's 161 characters in this file name, so it's quite a long file name. And it's a plain text file that's going to be pointed at by this thing. But there are going to be about 11 file name directory entries for that entire file name. The other one that I posted here is called toTextRoot, and this volume has just 2 plain text files in the root directory. So there's one that's called Iliad.txt and one that's called Odyssey.txt. These are just the epic poems by Homer. This is something that I just got from Project Gutenberg. They're just plain text files that have you know, actual content in them, and it's not just a bunch of random stuff. Maybe it is just a bunch of random stuff. I've never actually read these stories before, I don't know, but they're free, so here we go. The purpose of this one is going to be that this is going to be the volume that's used for testing. You can have 2 files open at the same time, and we can slowly step through each one of them one line at a time approximately. In terms of the assignment, I'm probably not going to be publishing any more sample volumes unless there are specific requests that people are making for, like, I want to test this condition with my code. I'm happy to make a new volume for you, but I think that the set of volumes that we have here is pretty comprehensive at this point. I'll talk more about this on Friday, but I'm also going to be publishing 2 more sample programs to go with cat.c. The 2 programs that I'm going to publish on Friday are ls.c, which does what you might expect it to do. This is a program that will list the contents of a directory. And the other one is going to be called paste.c. Paste is a core utils program. This is a program that comes on most Linux distributions where you can take 2 or more files, but I'm just going to limit it to exactly 2 files. And it will read 1 line from the first file and print it out with no new line, and then it will print the first line from the second file with a new line at the end of it. So it kind of like takes the 2 files and it puts them side by side in your terminal. 1 line, 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 1 line. And so I'll be posting these 2 sample programs up to the template repository on Friday, and we can take a look at those together on Friday to get a sense of what those look like. As promised, again on Friday, I will leave some time for questions about the assignment if there are any, but there's lots of people asking questions on the forum. There's lots of people asking questions in office hours. There are people been visiting Khaled, so he's happy about that because he's not just sitting there quietly you know, doing nothing for 2 hours. So that's really good. I'm happy that people are working on this, and lots of good questions are being asked. All right, so what I do want to do today, what I want you to be able to do by the end of today's lecture is continuing. I'd like you to be able to continue describing the life cycle of a process. Last class, we looked at some sample codes that that does stupid stuff like read a single character from standard input and then print that single character back to standard output. But that gave us the opportunity to inspect things like this process has a state and it gets blocked at this certain point. And that blocked, that's a keyword I'm going to be using over and over and over again in this course. This is a broader topic that we will be talking about called synchronization between different processes. But the word blocked here, in terms of the life cycle of a process, it starts to run, it gets blocked, and then it ends. This might happen repeatedly, but we've seen it so far kind of going through that with one loop of that. We're going to be continuing to describe how an operating system manages processes in terms of its data structures, control of processor, and modes. This control of processor part, this is more going to be in the textbook in the form of that limited direct execution chapter. So like the things that the operating system is able to do with the processor that our programs are not able to do with it. And that's related to mode switching. Today, we're going to be focusing on the idea of data structures. So what are the data structures that the operating system is using to represent a single process, and what are the data structures that the operating system is using to represent many processes that are currently running on the system? I want us to be able to also determine what an OS might need to know about a process. And so this is really directly tied with that whole idea of the data structures that the operating system is using to keep track of or manage processes. The last thing I want us to be able to do, and this may spill into Friday's class, this will probably spill into Friday's class, is I want you to be able to write code that uses system calls to manage a process. Last class, we looked at the use of fork. Fork allows us to ask the operating system to make a new process, basically by copying my process. Make a copy of this currently running process. And now we have two processes that are running. That's asking the OS to create that process, but there's very little value in that what we've seen so far. There's very little value in just duplicating a process and having it print the same message out twice. And so I want to spend some time looking at, well, how can we use these multiple processes to our advantage? And how can we get these multiple processes to coordinate with each other? How do we get them to synchronize with each other? How do I get one process to block based on the state of another process? How do I get it to do things like that? That's the thing, that's the last part that I want to do. And like I said, this will probably start to spill into Friday's class. Okay. So what I want to do here is I want to start determining what an operating system might need to know about a process. What I want to do here is I want to take a look at basic.io.c, and I want to step through this kind of in a line-by-line fashion. And I want you to tell me a little bit about, based on a line that we happen to be looking at in this file right now, what is our operating system responsible for keeping track of? What kinds of things does our OS need to keep track of for this? What I'm going to do with this is I'm going to open up basic.io.c on my screen here. Here it is. Is that big enough for everyone at the back to see? Should I make it bigger? A little bit bigger. Make it a little bit bigger. I've tried to change my Vim so that it is highlighting an entire line here. We're going to step through this line by line, starting at our main function. And what I want us to be able to do is to start saying things like, to do this line of code, an operating system would need to keep track of this, some kind of specific thing. The way that I'm going to ask you to do that is I've got a Mentimeter that I've prepared, and I'm going to start it just over here, and then I'm going to pop back over to this QR code. So I'll put this up for just a couple seconds, and then I'll switch to the Mentimeter itself. Okay, so I'm going to switch over to the Mentimeter. And what I want to be able to do here is I want to be able to have my terminal open with Mentimeter in the background, and I want to start looking at lines of code, and I want you to tell me about what kinds of things our OS needs to keep track of. So I'm going to go to the start of this file, the very top of this file, and I'm going to just skip these first two lines. These are preprocessor directives. This is not something that is happening when our program is running. This is just something that happens when our compiler is compiling our code. So we're going to get right to line 4 here. What kinds of things is our operating system responsible for keeping track of here for line 4 specifically? So I got process ID. I've got process state. I've got PC. I'm going to ask politely. I see program counter there, so I'm just going to connect those two things together. We have to have a program counter. In this specific example, I'm going to just like abstractly say that our program counter is the line number. It is not. You know, there's instructions here. There is a labeled section of our code that is the main section that points to a specific instruction in this compilation process, but I'm just going to abstractly say our program counter represents our line number right now. Runtime stack, yes, yes, yes. I'm actually going to broadly change this to be variables and memory. Just very broadly change this to variables and memory. I'm writing this down too. So I'm going to put my screen up. I just can't have like 15 screens open here at the same time. A function call. So the runtime stack and function call here, I'm going to connect together and say that we have a stack. Okay, state, program counter, variables for the process, location of the program in memory. Okay, good, awesome. We've got the code for the program itself. We've got our stack, yes, good. So we've got code and stack. Kernel or user mode. So that's a good thing to bring up here, but this isn't really something the OS is keeping track of. The OS will either have control of the processor or it will not have control of the processor, but it doesn't really have to know if it's in kernel mode or not. If its code is running, it's in kernel mode. If its code is not running, it's not in kernel mode right now. Heap allocated memory. So yeah, we don't actually technically have a heap right now, but one thing that we saw when we used that program called strace to print out all the system calls that our program is making, one of the system calls that we saw was a system call that is called BRK, break. We didn't call that. We didn't call that. The standard library called it. But that's the function that we're ultimately thinking about in terms of a heap. That's ultimately the function that we're thinking about in terms of a heap, which is where our dynamically allocated memory is going to go. We will talk about that later, but yes, I'm going to say that yes, we do need to keep track of our heap allocated memory once we're on this line. Okay, I'm going to move down here. Now we're on line 6. You should be able to enter new things here if you want. With Mentimeter, I tried to set it so that you can have unlimited entries here. So now on line 6, what might we be adding to this, if anything? Static variables, stack. So I think these are good things to have. Address of buffer and memory, yeah. This is a stack allocated variable, so it's going to fit into that stack structure that we've got. Really, really broadly, this code, stack, and heap structure that we're looking at is going to be called or referred to as the address space for our process. This will collectively be known as the address space for our process. Location of the variable memory plus its value. Yeah, good, awesome. Okay, I'm going to go down to line 8 here now. Now that we've got line 8, what might our operating system need to keep track of on our behalf to be able to satisfy this, to be able to print something out to my terminal? The standard IO file descriptor, standard out file descriptor of standard out and buffer. Yeah, okay, so awesome. I'm going to generalize this to say that we're going to have an open file table. We're going to have an open file table for this process. And one of the entries in this open file table is going to be for standard outputs. Standard IO, file descriptor, end of line character, program counter from main function. Okay, good point. Yes, the program counter has changed. The program counter has changed, and our operating system doesn't directly need to track that. But on this specific call, on this specific line, that program counter will have changed, and we're doing this whole transition from user space to kernel and operating system space. We're doing this mode switch. And as part of the mode switch, our processor is going to do stuff like save the registers, the values of the registers, just before we did the mode switch. Once we enter our operating system space, our operating system is going to complete doing this. It's going to save the rest of the registers that it needs to save, but one of the registers that's going to be saved as part of this process is the program counter, so that when I go back to user space in this process, I'm able to set that register. The OS is able to set that register again so that we can keep going on this same line that we're on right now. The status of input, what was entered, that will be something that we'll get to in just a second. One thing that that's out of scope for this course that I'm going to add to this for us so that we all know is that our operating system, as part of standard out here, it's going to have its own system table. This is a little bit harder to see. This is its own system level open file table. So we're going to have an open file table for the process, and we're also going to have an open file table for the entire running system right now. In my terminal here, I've got a bunch of output that's been printed. So like, we think of Vim here as a program that's doing really magical stuff. I think of Vim as a program that's doing really magical stuff. But if we get down to it, ultimately, to get this line of output, Vim is doing a write. To get this line showing up on my screen, Vim does a write. To get this 3 to show up on my screen, Vim does a write. It's just making these same system calls that we're working with to be able to do this stuff. Don't get me wrong, there's lots and lots of layers of abstraction here, but Vim is ultimately making the write system call to put these characters in our terminal. This is called a terminal, okay? Yep, we were all agreeing on that. Okay, it's a terminal. The operating system needs to keep track of all of the terminals that I have attached to this system right now. I'm using tmux, and I have at least 3 terminals here that are attached to the system, but there's actually like panes within here, so there might be 7 or 8 different terminals that I have attached to the system right now. When you are all connecting to Aviary, one machine on Aviary might have like 15 terminals all attached to it right now, where it's your terminal window that's attached to it. So we've got standard out. Yes, we do have standard out as an entry in the open file table for this process, but standard output here is also connected to our open file table at the operating systems level, so this global open file table. And that standard output entry is going to be connected to something like, I'm going to annotate this in my notes here as TTY1, teletype terminal 1, TTY teletype. And this is like literally characters that are being printed out on a keyboard typewriter, an actual literal typewriter. But we're getting it connected to this thing so that we see stuff here. Okay, so that's awesome. We've got an open file table in our file, an entry in our open file table to represent standard output that is connected to our system table that represents TTY1. I'm going to skip these comment lines because they don't actually do anything in our program. So now we're on line 12. What's happening here? What does our operating system need to keep track of to be able to satisfy this line? English or Spanish? I was thinking about this in terms of like wide characters versus non-wide characters, like Unicode versus ASCII characters. And I'm willing to be proven wrong on this, but I'm going to say no, it doesn't keep track of that. It will keep track of it in terms of the locale, but that's not something that's happening at the OS level. That's something that's happening in our standard library. So the thing that's responsible for printing characters isn't really going to necessarily know that much about it. The status of input, so what was entered? This was something that was stated for the last time. This is going to be something that we're going to have yes. The state, so we've got the state here, and the state will have changed now. So the state went from running to what? Just shout it out. All of us, let's all shout it out, so it's not one person saying it. Blocked, thank you, yes. We went from running to blocked, okay. We went from running to blocked. Status of input, what was entered? We've got standard IO file descriptor, standard out file descriptor. What file descriptor is getchar using? Standard input? 0, 0. I forget which number it actually is. It is 0 or 1, but yeah, it's one of those two. Standard input. Okay, so we have another entry in our open file table here for standard input. And this is also going to be connected to our global open file table, and it's going to be connected to the same terminal. It's going to be connected to the same terminal in terms of getting input from this thing. I'm going to go down to this line right here, and I'm going to ask again, what does our operating system need to keep track of here to be able to do this call for us? If anything else is new. I don't really think anything has changed here very much. Yeah. There's another page. No, there's no slides. They're not updating. I have been scrolling. I'm just going to present again. Okay, all right. Thank you for letting me know that it's not updating. Yeah, thanks for letting me know that it's not updating. Okay, so can't think of anything more. Were you all writing the file descriptor for standard in, as I'm saying here? Like, I'm sorry, I'm really sorry. I'm really, really sorry. Okay, so wait for standard input. How much space is in memory after left recording the value of the input, standard out, update the address location, location of buffer in memory, the file descriptor of standard output, update context and address location. Yeah, so the file descriptor of update of putchar is changing the location of the file descriptor in standard output, changing the location of standard output right now. Okay, I'm going to go down to this last line, and please immediately let me know if this is not updating. We're returning now from this program. We're ending this program. What does our operating system need to keep track of here? Exit stuff and halt. Okay, so it's updating, good. The program counter of the previous function, freeing the memory, popping the stack and journal status. What data was allocated for this program to clean it all? Stack memory that needs to be removed in the heap. How do I redirect output to another terminal? Is that a question, or like, I don't think it's a question. More of like, how do I take that output and send it to a different terminal? Memory stack, the process state again, final, so it's coming to ended. Yes, I'm going to pick on this one specifically. What data was allocated for this program to clean it all? There's two different kinds of memory that's being allocated for this program now. There's the memory that's allocated for it in its address space. So its code region, its stack, and its heap at the very bottom. But the other thing that's being allocated is in the operating system side. In the operating system side, what we've got is this structure that represents all of this stuff that we've got here, all of the stuff that we've got here. And this is that thing that's called the process control block. This is the data structure that's representing everything about a running process right now. So as part of this program exiting, our operating system is going to have to say all the memory that this program allocated, whatever it is not used by that program anymore or that process. And then internally, it's going to need to say, this process is gone, so I don't need to keep track of it anymore. Okay, awesome. Thank you all for participating in that. AI tools are not available. When I was making this, there was this nice shiny button that said, request access to use this AI tool to auto summarize all the responses and auto group them. So I clicked the button to request access, and then I saw it here, and I'm like, awesome, I can try to use this in class today, and apparently not. No, I can't. Okay, thank you all for participating in this Mentimeter. What I am going to show you here is what I wrote down. I will share this document with you, so if this is slightly different than what you took, you'll have another copy of what's there. But we've got a process ID, so this is some unique number that represents the process. We've got the state of the process, and it's gone from running to blocked, and then back to running again. So we've got this kind of cycle, or the cyclical process that this process is going through in terms of its state. We've got the program counter, which we're abstractly going to say is the line number in the C program, but in reality, it's going to be whatever instruction it's currently executing on the processor, or the next instruction on the processor. We've got this really big abstract idea of memory, and what I'm going to say here is that this is the address space for the process. So that's the word I'm going to use to describe this whole idea of code stack heap is address space. This is the address space for this thing. And then we're going to have this open file table structure. Our open file table structure for the process has references for standard out, standard in, and then it's also got one for standard error. And each of these are going to be pointing at a system level open file table, where the system level open file table is, at least in this case, referring to a terminal. It's a terminal that's producing output and getting input for us. It's going to have to keep the location of where in this file-like thing so that when I do get char, I don't just keep getting the same char over and over again. I get the next char every time there's a new character that's entered. The program that we had gets exactly one character, but if we wrote a program that put get char in a loop, it would keep getting the next character in this input that we have on standard input. It wouldn't just constantly give us the same one back over and over and over again. Okay, so awesome. This is great. This is a really good idea of what our process looks like from the operating system's perspective. Our process doesn't need to know anything about what our operating system knows about it. Doesn't really need to know anything about it. But our operating system has to keep track of all this stuff on our behalf. I'm going to come back to this in just a second. And what I want to do now is spend a little bit of time thinking about, we've got this fork system call. What's actually happening in the operating system side? What is the OS doing in terms of the data structures that we've got? So I'm going to pop back over here, and I have pre-prepared this And the code that I've got here on the left is pseudocode for processmanagement.c. I've omitted all of my semicolons and curly braces and stuff, and I didn't even call printf. I just put print here. What I want to do with this is I want to start at main, and I kind of want to step through here, getting to the point of fork and trying to make some decisions about what our operating system has internally in its own data structures. The first thing of note that we've got here is that our operating system is going to have this process list or this task list. Abstractly, right now, we're going to say there are no processes running. That can't actually technically be true because the OS has to be running at some point on the system, but we're just going to say that there are no processes running in this system right now. When I get to line 1 here, in this program that I've got, that is my pseudocode representation of processes.c, my operating system is going to start creating a new entry in this task list, in this process or task list. The values that are in this process or task list are going to be the process control block for this process. So in terms of the stuff that we had seen just a moment ago, that's going to include things like the program counter, the register set that we have for this process right now. And I'm going to say that the program counter here, the value is going to be 1. This is the next instruction that you should execute for this program. The other thing that we're going to have open immediately in this thing is an open file table. And we're going to have entries in our open file table, and please don't quote me on the actual order of these. This is just for illustrative purposes. We're going to have entries 0, 1, and 2 for std in, std out, and std err. And each of these are going to have some kind of a reference, so some kind of pointer type structure to the corresponding entries in this system level open file table. We are also going to have some memory for this process that will have been allocated. And so we're going to have argc, argv, and envp. So some space will have been allocated for this. Our stack variables. They're going to have some values. We're going to have a state for this process, and we're going to say that it's running. If we're entering the first line of this process or the first instructions for this process, it's safe to say that this process happens to be running right now. When we enter this code in our process, the operating system loses control. It doesn't have control of this processor anymore, and our code is going to take over. The contents of memory are still going to change kind of in the operating system side, in that it's memory that's kind of central to the system. All of the processes are ultimately sharing the same physical memory structure that we've got here. So as we change our program counter here from 1 to 2, we're going to add this new PID value, and we're going to say that it has a value of -1. As we change our program counter to line 3 here, we're going to have another entry here in our stack that's for letter, and we're going to say that it's going to have a value of W. And then on line 4, when we enter this line, now we're going to give control back to the operating system. Our operating system is going to do things like persisting what the state of the registers are right now for this process. And then it's going to ultimately satisfy this write request to standard output. So our operating system is going to have to make some changes to the output for this teletype terminal that we've got here to move its basically move the print head over one spot so that we can print these characters out. Once we're finished doing that on the operating system side, we go back to the user space process here, and we're going to start executing our next line of code here. Once we hit line 5, this is where the magic starts to happen. The magic starts to happen here, and the way that the magic is going to happen is that we're going to enter the operating system space. A fork request is literally, please duplicate this process control block. So our OS is pretty much going to say, all right, I have the benefit of copy and paste operations here, but our OS is going to be able to say something like, I would like to do a mem copy, for example, of the structure that I've got for this process control block. And what I'm going to get here is a new entry in this process or task list that has entry number 1. This is the new process that I've just created. We're going to be able to set registers, return registers in this case. So thinking back to Comp 2280, when we did a call, we had to take things out of the return register from the function that we were calling. Yes, yes, yeah. So when our operating system is giving control back to each of these 2 processes, because now there's 2 processes here, it's going to put a different value in that return register for each of these processes. They're both at line 5 right now, but what we're going to do is the return register that gets moved into what PID's value is will change. In the child process, the new one that I just created, the value is going to be set to 0. So on x86, this will be like register EAX or something. We're going to move EAX into whatever address location represents what PID is, and that value will change to 0. In the parent process, when that one gets to run, our operating system will have changed the EAX register in its own representation of the register set in the process control block, so that when we get to finishing line 5 here, the value that we're going to set here is 1, the ID of the child process. So our OS is going to change the value of the registers in its own process control block, then switch back to the user process, and the different user processes that we have, these duplicates, are going to have different values in the variables that we've got here. So now, in terms of abstractly running this, I'm going to say that we're operating piecemeal here. We're going to take turns. Each process is going to get a turn on the processor. We'll spend more time talking about this when we get to thinking about scheduling. But what we'll say is the parent process gets to go to line 6. And on line 6, we're asking a question about the state of this variable. We're asking a question about the value of this variable. In this process, that value doesn't actually satisfy that branch condition that we've got. So we're going to skip over the contents of this thing. And our next instruction for the parent process here is going to be number 9. On number 9, what we're doing is changing our state to blocked. We're halted here. We are waiting. We've asked for input on standard input. So getchar is asking for input on standard input, and I haven't typed anything yet. And so this process becomes blocked. And now the operating system is going to be able to say, all right, now it's the next process's turn to run. We're now going to be looking at process 1 here. Process 1 currently has program counter 5. It's still up there, and it's about to move to our next line of code. We've changed that PID, and so we're going to be starting to work on line 6 here. In this process, the code is still the same. We duplicated everything about this process. So the whole address space is the same, the code is the same. But the value that we got back from that register, that return register, is different. And so the value that we have in PID is different. And so now we're going to execute different instructions in the same code. We're going to say if PID is equal to 0, it is. So we're going to go to line 7. And on line 7, we're going to say letter is equal to C. So this is moving a constant literal into our stack memory here. So I'm going to be changing letter here to C. But we're not changing it in the parent process because we have these distinct copies of all the memory that we've got for that parent process when we did the fork in the first place. Then we're going to print out child here. And when we print out child here, our operating system is keeping these references to this open file table, the system level open file table. And the print is going to print to the same terminal that our parent process had in the first place because we're pointing at the same thing. So it's going to print the word child here. So I'm really sorry, I should have been updating our output. We would have seen hi, and now we'll see child. And then after we finish doing that print statement, we're going to move to line 8 in our child process. And we're going to hit get char. And get char is going to change this process's state also to blocked. So now we've got these two processes that are both halted. They're waiting for input on the same standard input here. Both of their open file tables are referring to the same TTY1. And so I'm going to hit enter on my keyboard once. Which one runs, 1 or 2? Show of fingers, 1 or 2. On the count of 3. 1, 2, 3. 2 wins. Okay, 2 wins. So 2 gets to go first. So 2 gets to go first. It will become unblocked. It will go back to running again. Then we're going to immediately go to line number 10. So this should have been 9 and then 10. And now we're going to print out the letter here. So we're going to print out the letter C from this process's address space. Then we'll get to line 11. And then we will be exited. And then I'm going to hit enter on my keyboard again. And now process 0 is going to become unblocked. It will be running again. It's going to print out its letter, so it will print out W here, and then it will go to line, so it'll go to line 10, and then it will go to line 11, and it will exit, and our process's state will change to exited. And now our operating system is going to have to go through these, and I'm not going to erase them because I want to actually share this with you. Our operating system will go through this, and it will erase these process control block entries from its process list. These are not running things anymore. They're done. They're all finished. This program is finished. It's exited. It's over. It doesn't need to keep track of this stuff anymore. All right. How are we doing? Is that okay with everybody? Any questions? All right, okay. This decision-making process, 1 or 2, I guess it was 0 or 1, sorry. I was making it more confusing than it needed to be here. This decision-making process is the scheduling process. We will see this later. For now, it was an arbitrary decision. It's a random decision which one gets to go, but there is actual algorithms and policies that state which one would get to go next that we will see later in the course. So I'll post this, these documents for you so you'll have a copy of them up on the course webpage. What I'd like to do now is in the last 5 minutes of class, so this will spill into next class on Friday, but for now what I'd like to do is spend some time thinking about managing processes. We're going to do this in a few different ways. I want to look at the following. I want to look at the weight family of functions. There are 2 different weight functions that we'll be able to call. And weight functions very generally are going to be calls that will cause a process to become blocked until something happens in another process. So the word that I'm going to use to describe this is, I'll continue to use the word blocking or blocked, but I'm now going to start to add the word synchronization between processes. Synchronization between processes. This will probably be on Friday, the exec family of functions. So fork causes a process control block to duplicate. The exec family of functions are going to cause the code section of our process to change to something else. Let's take a look at wait. So I'm going to go back to my terminal here, and I'm going to expand my terminal. I'm going to quit basic IO, and I'm going to open up processmanagement.c here. So processmanagement.c, just to help you remember where we were at last time, what we were doing for this was we had created some variables. We printed a message. We caused our PCB to duplicate. We asked a question about which process we were in, and then we caused this to block at the end of the code section here. What I want to do here is I'm going to cause my child process only to block. I want it to stop. So I'm going to delete getchar from here, or I'm going to comment out getchar from here, and I'm going to add a getchar here. We're executing in the child process, and I'm going to say printf. Whoops. No, I don't want to look at the help. In the child process, my process ID is, and we didn't see this getPID call, but getPID is a way that a process can ask a question about what its process ID is. This just returns the process ID for that process. Enter a letter. And then we're going to go into a blocked state here. If I compile and run this code, what we're going to see here is that there are two processes currently running. There's the parent process. I'm going to actually quit this. I'm going to make this again. I'm going to write this. I'm going to make this again. And then I'm going to run it. And what we've got here is the state that is our child process is blocked. If you remember last time, I had to press enter twice for my code to finish. And what I'm able to do this time is enter once, and both of our programs will immediately finish. I'm going to add a new call here that's to a function that is called wait. Wait is a function that will cause a process to just block until the status of its child process or until the status of a specific process has changed. Typically, this is going to be from running to exited to finished. I'm going to add some code here in an else block. In the else block, what I'm going to say is wait null. I'm going to go up to my top and come back here for just a second. I'm going to add number include syswait.h. And I'm going to go back down to the else block here. And what I'm going to say with this is printf in parent waiting for child %d. And then what I'm going to put in this output is the PID that I'm going to wait for here. Wait with null I'm not in the right directory. Wait with null, we'll come back to this on Friday. Wait with null says, wait for any child process. There was only one child process. This will cause us to block until the child process exits. This will cause us to block until our child process exits. So we'll get stuck in this sleeping state until our child process is finished. We're going to revisit this on Friday's class. But at this point, what you should be able to do is you should continue to be able to describe the life cycle of a process. You should have a little bit better of a sense of what a process looks like, especially in terms of not just going from running to blocked to ready, or ready to running to blocked to ready to blocked to ready to blocked to ready to exited, but now also duplicating our process control block. This is how all processes are ultimately going to be started. You should better be able to describe how an operating system manages its processes, specifically in terms of data structures. We've been able to determine what an OS might need to know in terms of managing a process, and you should also be able to start to use system calls that manage a process. That's it for today. Thank you all for coming out, and I'll see you on Friday. Bye, everybody.